Today, we're not going to do everything with complex numbers, but we're going to do a quick basic review. There's a lot more to complex numbers than we're going to look at today. We will get to some of that really neat stuff later in the course when you have some more background that you'll need. So we start looking at this equation, x squared plus 1 equals 0. And in the real numbers, we don't have a solution for this. And you might think we're just making something up. Well, we are. We're kind of making something up. We're making up this new number we call I. And what distinguishes it is that I squared equals minus 1. So we call this the square root of negative 1. Now, again, you might think we're just making something up. We talked, I think, a little bit, can it be useful? You know, actually it turns out it's useful. But it might be worth pondering the fact that all the other numbers are just something we made up too. I mean, it's hard to get a handle on that because from the time you're like 2 or 3, your parents are going, count 1, 2, 3, 4. Numbers seem very real. They're really useful, but you're never walking down the street and trip over a number. In your head, you might, I suppose. So all these things we're dealing with in mathematics are abstract concepts which are useful. And I mention that because a lot of people, when they come across this, it sounds like this is nonsense. You can't multiply a number by itself and get negative 1, because if you multiply 2 negatives, you get a positive. 2 positives, where does that come from? But we're at the point in mathematics where some of the things we come up with, they may not make sense right away. It may not be clear that they're useful. And I'm going to show you something, hopefully, at the end of the day, where it's not even as useful. It's incredible to look at. It's really neat. So, all right, that's my little song and dance on complex numbers. Fine. I guess that's an imaginary number. A complex number we define as a number a plus bi, where a and b are real numbers, and I we define as the square root of negative 1. So that's our complex set of numbers, which again I'll sometimes indicate by this stylized C. It's this set. Okay, from here on, if you just keep this in mind, that I squared equals minus 1, everything else fits into place real easily. So if we wanted to add 2 complex numbers, say 5 plus 2i and 6 plus 3i, well, that's straightforward. We just add the real part and the imaginary part separately. 5 plus 6 is 11. 2 plus 3 is 5. Multiplying is a little, there's a little trick in there, but it shouldn't be too hard to grasp. We're going to use our FOIL strategy here. So our firsts, 5 and 6, are 30. Our outer is 5 and 3i, so 15i. Our inner, 2i and 6, is 12i. And here's the tricky part. 2 times 3i squared, so that's 6. But the I squared gives us a negative. That's negative 6. So now we just have to combine the terms. 30 and minus 6 is 24, and 15 and 7 is 27. So that's how we multiply complex numbers. Yes?
Can you move that thing down? Because I can't see.
I will when I find the trick. Well, the trick is to not have this stick back there.
Thank you.
Okay. I didn't even mention subtraction because everyone should know subtracting is just adding the opposite, right? This was a minus, right? It's just adding minus 6 and minus 3i. So the obvious next thing we want to look at is dividing. But before we look at dividing, we're going to first take a look at a concept related to complex numbers, something called the complex conjugate. We have a complex number, a plus bi, and the complex conjugate is just a minus bi. All you do to find a complex conjugate is reverse the sign on the imaginary part. That works just as well if you've got a real number, pure real number, or a pure imaginary. The complex conjugate of 5 is 5. The complex conjugate of 2i is minus 2i. Now, this is actually a really, really neat and useful idea. The reason is, what happens when we multiply a number by its complex conjugate? Let's take an example. Let's say 3 minus 4i. Its complex conjugate is 3 plus 4i. Now this looks a little like our pattern a squared minus b squared. A squared plus b, a squared minus b squared. But it's going to come out a little differently. All right, let's multiply the first, that's 9. The outer plus 12i. The inner minus 12i. And then the lasts, 4 times 4 is 16. It's minus 16 I squared, so it's plus 16. The thing to notice is that the imaginary part's always going to drop out. So we're just left with 25. So one of the useful features we're going to find for the complex conjugate is if we want to change a complex number into just a pure real number. Okay, so that brings us to the subject of division. So let's take a division problem. Take 5 plus 3i divided by 2 plus I, or I'm going to write it the way we often will write it, as a fraction. So to figure out how to do this, we have this ugly denominator we don't really know how to divide yet, right? We're trying to figure out. Let's get rid of it. Let's get rid of the complex number here and make it a pure real. So we do that by multiplying by its complex conjugate. But of course, we want to multiply by 1. So what do we get here? I guess I want to enshrine this in a pattern here. What happens if I multiply a plus bi times a minus bi? Well, the inners and outers will cancel. Let's make these capital E's to make it nice. The firsts are a squared. The lasts are minus b squared I squared, which is just plus b squared. So, pearl of wisdom here is now, if we have complex numbers at our disposal, we can factor this. This is a plus bi times a minus bi. You want to be careful you don't confuse this with our a squared minus b squared pattern, right? This is always going to give us a complex number with an imaginary part. All right, so this tells us this is going to be 2 squared plus 1 squared, or 5. Now I just have to do a multiplication. 10 minus 5i plus 6i, so minus 3i squared plus 3, or 13 plus 5 over 5. And depending on the circumstances, you might want to leave it in that form, or you might want to put it into, well, I erased it, but into our normal complex form, which would be 13/5 plus 1/5 I. It's the normal form we put a complex number in. Okay, I'm going to pause just a second because I see people come in late, and I'm just going to go through the list real quickly. Nico, Amsita, Al Yang, Jason.
Yep.
Jason's here. Stefan Ramsey. Okay. Albert. Bakane.
Here.
Back. Okay. How can? Is that you? Okay. Jackie. Yugi Young. Alexis. Sophie. Charlotte. And Elixir. People came in late. I have homework. End of class. Come up and do your homework. Oh, that's weird. I'll just put my notes down somewhere. Oh, here they are. That's what my wife calls doing a Mitchell. You put something down, you put something on top of it, and then you go, Elva, where did you put this? So that's doing a Mitchell. Okay. We're almost done with complex numbers for today. I want to point out something important. Clearly, I squared is minus 1, but it's good to keep in mind that negative I squared is negative 1 squared times I squared equals 1 times negative 1 squared is 1, and I squared is negative 1 is minus 1. So I squared isn't the only thing, isn't the only square root of negative 1. Also, is also equal to negative I. That's important if you have an equation that, let's take a look at, say, x squared plus 4 equals 0. Well, now I know that I can factor this. This is x plus 2i times x times x minus 2i. So x is either equal to 2i or negative 2i. That is to say, it's a second degree equation and it has two roots. All right. Going back for a second to the quadratic formula, we have ax squared plus bx plus c equals 0, which has solutions x equals negative b plus or minus the square root of b squared minus 4ac to a. And we look at the discriminant, quantity here, and we discover that the discriminant might be now less than 0. That tells us that this is going to be imaginary. So we're going to have two solutions. Let's just take an example. Say x squared plus 4x plus 5 equals 0. So x will be equal to negative 4 plus or minus the square root of 16 minus 4ac all over 2, or negative 4 plus or minus the square root of negative 4 over 2, or negative 2 plus or minus y. The thing I want you to notice is that whenever you have a quadratic equation that has complex solutions, what we see about those complex solutions are always going to be complex conjugates.
Say that again?
Whenever you have a quadratic equation, the discriminant is less than 0, so the solution is going to be complex number. You're going to get two roots, and they will be complex conjugates. That is, think of a as negative 2, b as I. The solutions are a plus bi, a minus bi. These two are complex conjugates. You always get this plus or minus on the imaginary part. Always. Okay. That's it for complex numbers for the moment. Any questions before we move on? So we're going to change gears for a little bit. Okay. You're going to have to talk loud too. For me to go over those.
So you know the dividing, example we have there, 5 is, it's not there, 5 is divided by 2i. So when is it that you use the reciprocal for dividing rather than multiplying its opposite?
That's a good question. We didn't talk about it in terms of complex numbers yet, but let's make up something, all right? Let's say I had 3 plus, I'm making this up as fast as I can, 1 plus 5, and I want to divide that by 2 minus 4i over 6 plus 2i. So I want to divide this by this. I can write it this way. I have a feeling some people at one point were confused. You don't really clearly draw a big line here. And here's an example where you would want to multiply by we want to divide by multiplying by the reciprocal, right? So essentially what we're doing here is we're saying, let's take the reciprocal of this, multiply the bottom by that reciprocal. And we want to multiply by 1, so we have to multiply by reciprocal over the reciprocal. And we don't usually do this part because we know this is just going to be 1.
So it's only reciprocal if it's a fraction divided by a fraction, not like a number.
Let's say I had 2 divided by 1/3. I can multiply, I want to divide by 1/3, so I multiply by reciprocal. Again, this becomes 1, and that's the reciprocal of a third, so that's just going to be 6. Okay, I guess I don't have to finish this. What I would need to do to finish this is, what I need to do. Well, I probably need to move this out of the denominator, multiply I minus 1 minus I over 1 minus I. And the same here, 2 plus 4I over 2 plus 4I. And then I'll just have real numbers on the bottom and something very complex on the top. You know.
So instead of starting from there and working off that, you get rid of that denominator on both sides? Is that what you're saying?
Oh, no, you don't have to. Well, you could do it either way. You could multiply first, and then I'm going to have a complex number in there. Should I do it?
Yeah.
Yeah, sure.
Okay. All right, so, yeah, I could do it either way. Yeah, it's probably saves time to just do the multiplication first. All right, let's FOIL the top. All right, so 18 plus 6I plus 12I minus 4.
4i squared.
4I. No, minus 4. 2I times 2I is 4I squared minus 4. FOIL the bottom, 2. Outer minus 4I plus 2I. And now, minus 4I times I is minus 4I squared, which is plus 4. Okay, so we have 14 plus 18I on top. And here we have 6 minus 2I. Okay, so now we want to multiply by the complex conjugate of the denominator here over the complex conjugate. Okay, we know this is going to be 36 plus 4. A squared plus b squared. So that's just 40. And then I have to do one more FOIL here, which will challenge me here. 684. 28I. 6. $108. Can't think and write at the same time, apparently. And minus 36. So 84 minus 36 is 48 plus 136I over 40. We've got at least a factor of 4 in there, right? 12 plus 34I over 10. It's another factor of 2 still. 17I over 5. So this is 6/5 plus 17/5 5. It's like a game show. Stump the professor.
I like when you slow it down. I was doing this last night and it was like way faster than that. It looked like chicken scratch.
Yeah, if you want me to, I'm sorry. Shall I do it slow?
No, you already did slow. That's what I was saying. Last night it was like with a supercharger on it.
What was last night?
When I was doing it at 2 a.m. with my roommate.
Yeah. Okay. All right. Okay. We're going to look now at inequalities. Instead of an equal sign, we're going to replace it with one of 4 signs you should be familiar with. Less than, greater than, less than or equal to, or greater than or equal to. And we have some basic rules for dealing with inequalities. A is less than B, then A plus C is less than B plus C. That is, if you have an inequality and you add something to both sides, it remains an inequality. I can replace less than with any of these 4. If A is less than B and C is greater than 0, then AC is less than BC. That is, if I have an inequality, I can multiply both sides by a positive number and I don't change anything. Again, that's for all 4 inequalities. But if A is less than B and C is less than 0, then something happens here. The inequality switches direction. A less than would become a greater than. A less than or equal to would become a greater than or equal to. And the reverse, greater than would become less than. Let's just take a silly, just so abstract, let's just say 5 is less than 3. If I multiply both sides by -1, I get -5. Well, I'm saying that has to be greater than -3. Well, that would have worked, except I wrote something silly on the board, didn't I? 5 is not less than 3. 5 is greater than 3. -5 is less than -3. That's not the only thing we can do to flip the inequality sign. Given that A is greater than 0 and B is greater than 0, and A is greater than B, we look at their reciprocals, find the reciprocal of both sides. 1 over A is less than 1 over B. Okay, simple example, 5 is greater than 3. 1/5, of course, is less than 1/3. So what do we have? We've got 1 rule, 2 rules, parts A and B, right? And we have a 3rd rule here. Okay. If we have A less than B and C less than D, we now have 4 quantities. I can add the lessers and the graders and maintain that inequality. Kind of makes sense. All right, and finally, I'm not sure if this is going to come up anywhere in this homework, but we have the ever-present transitivity rule, which says A is less than B, B is less than C, and A is less than C. In other words, if B is in the middle of A and C, obviously A is going to be less than C. Does anyone here remember having difficulty with inequalities? I mean, I think it's pretty straightforward. You know, the place people usually get messed up is here when you multiply by a negative number. You have to remember to switch the inequality sign, but I think it's probably mostly straightforward. Okay, you haven't already memorized all of these before I erase them. We're going to work with these a little bit just to see how they function when you're trying to solve an equation, not an equation, an inequality that's a little more complicated. Okay, let's take a look at this. We want to solve this and sketch it. So we can go about this a couple different ways, but I'm going to start off by subtracting 9x from both sides, because I like my x's on the left. Not important, but I do. So we have minus 6x is less than 4. You know, because I can add or subtract the same thing from both sides without changing the inequality. Now I'm going to divide both sides by minus 6. Well, since it's dividing or multiplying, right? In other words, I'm multiplying by 1 over negative 1/6. This is going to reverse and become greater than. So I end up with negative 2/3 here, and I end up with x here. I might write this answer as the interval, negative 2/3 to infinity. Or I might write this as x such that x is greater than minus 2/3. Write it as a set. And now I want to graph it. So I'm going to draw a number line. Origin. And the only point I really need is minus 2/3, which since I don't have a scale, I can really put it anywhere I want. But this is greater than, not greater than or equal to, so I hope everyone knows we indicate that by drawing a little circle, meaning everything but that point. And I'll indicate this in the graph by trying to pick a line. So that's how I would solve this and graph it. Everybody comfortable with this? Is this new to anybody? Something new? Okay. Oh, question?
On my homework, I highlighted like the thicker line, and then whoever graded it wrote hard to see yellow. So should I not?
Yeah, that was me. I wasn't. I was just subtly complaining.
Okay.
It was okay. It was right. Yeah, but it was just a very light yellow. But you know, actually, I have a grader working for me now, so she has better eyesight. So you probably won't get too many of those complaints. Okay. All right. Let's try something like this, a little more complicated. Let's take 3x minus 2 is greater than or equal to 4, but also less than 13. sometimes you have to break these up into 2 pieces. 3x minus 2 is less than or equal to 4, and likewise 3x minus 2 is less than 13. You might have to break it up and work out each problem separately. But in this case, we don't have to. It's possible. We're just going to do everything in, kind of one long step here. So we'll start by adding 2 to both sides. And we want to isolate the x, right? So let's get rid of that 2. 6 less than or equal to 3x less than 13. My inequalities stay the same because I can add the same value to each of these.
15.
Yep.
Oh, thank you. Now I want to divide both sides by 3. And again, since I'm dividing by a positive number, I'm multiplying by 1/3, the inequalities won't change, and I get 2 less than or equal to x less than 5. I might write this as the half closed on one side, half open on the other side interval, 2 to 5. Or I might write it as a set x such that x is between 2 and 5. And again, to graph it, this hand is not cooperating. Okay. I need 2 points, 2 I'm going to fill in because 2 is included. And 5 is not included, so I leave it. I'm exaggerating here, of course, but and that's my graph. Okay, that's the easy stuff. I'm going to do the hard stuff. What happens if you have an inequality that is quadratic or otherwise it's nonlinear? X cubed, x to the 4th. How do we deal with that? Well, let's take a look at an example. X squared minus 5x less than or equal to minus 6. So the first steps we want to do are the same steps if this was an equality. Right? We're going to put everything on one side. And we want to see what the roots of this is. We want to factor this. So this is x minus 3 times x minus 2 is less than or equal to 0. So now what we want to look at is what I'm going to call critical points. Critical points are either where we get 0 or we get undefined. So in this case, we have points 2 and 3. These are our critical points. And now we break the problem down into checking each region and each point. So let me do this as a table here. So the first thing I'm going to check is down here less than 2. So I want to check something easy. So a good easy thing is often 0. If I plug in 0 here, I get 0 is less than or equal to -6. Well, I'm just going to write false. So stuff down here is not a solution to this. The next thing I'm going to do is try the point 2. Well, I know 2 is going to equal 0. Right? I'm sorry, did I just say that? I know 2 is going to make this side 0. So if I go back to the original equation, I'm going to just get -6 is less than or equal to -6. So that's true. Now I want to try the region between 2 and 3. So 2.5 is 5/2. It's a little tedious, but you actually have to check. In this problem, I think, when you see the answer, you go, yeah, okay, that was going to be. But in the next example, it's a little more complicated, and you'll see why we're checking all of these. Okay, so 5.5 minus 3, that's a positive number. 5.5 minus 2, that's a negative number. So I'm going to have some negative number less than 0. I'm not even going to look into it. You can see that's true. Similar to 2, I can plug it in. I know I'll get -6 on both sides. So this is true. And then the last region I might want to check might be out here, say 4. So 4 minus 3 is 1, 4 minus 2 is 2, 2 less than or equal to 0, false. So that tells me that the solution for this is where it's true, is the interval 2, 3. Again, I could write as x such that x is between 2 and 3. And as before, I can graph it. I just need my 2 points, 2 and 3, as the part of the line between these two that I'm interested in. Yes?
Checking it out, right, with critical points, checking that. What else does checking points and help with later other problems?
Good question. I had something like this. Okay. So let's multiply both sides by x minus 1. So we get x less than 3x minus 3, or minus 2x less than minus 3, or x greater than 3x. Well, I'm missing something here, right? There are two regions, right? Clearly it's x greater than 3/2. There's a critical point here, which is 1. So this is going to be x greater than 3/2, but x is not equal to 1. Now, 1 is less than 3/2, so it turns out that's not a problem. So my example wasn't very good. But you can kind of see where instead of greater than 3/2, if it's greater than 1/2, you would have to say x not equal to 1. All right. One more problem like this. complicated enough to see, you see that you have to be careful. Let's take x times x minus 1 squared times x minus 3 is less than 0. Well, this is nice. It's already factored, so we already know where the critical points are. 0, 1, and 3. I guess I'll put the line up here. So I'm interested in what goes on at 0, what goes on at 1, what goes on at 3, and now I've got also, I'll just label them A, B, C, and D, 4 regions. Okay, again, I'm going to make my table a little simpler. So if I'm less than 0, let's try minus 1, right? Okay, so minus 1 squared, that's positive. Minus 1 minus 3, that's negative. And a minus 1 here, so I've got 2 negatives. I get a positive less than 0. So this is negative 1, that's my A region, that's false. Okay. How about 0? 0 less than 0, that's false. Now let's take the region in here, which is, we'll take a half, okay? You notice I don't actually have to figure out the whole number, I just have to, since this is just, it's either going to be less than or equal, less than, greater than, or equal to 0, I just have to figure out the sign. So 1/2 minus 1, it's a minus a half squared, that's positive. One half here, that's also positive. 1/2 minus 3, that's negative. So here I am going to be less than 0 in this region. So I already know I'm not including 0, and I'm going to include this region. Let's take a look at 1. Well, it's 0. The whole thing is 0, so this is false. So I'm going to have a hole here at 1. This is my B region, right? And now I'm going to try, over here I'm just going to try 2. My C region. So 2 is positive, 2 minus 1 squared, that's positive, 2 minus 3, that's negative. So the C region is going to be included. And try 3, well 3 is 0, so that's not included. So again, I have a hole here. And finally, I want to check my D region, so I'll try 4. Notice I'm just using the simplest numbers I can. And when you're doing homework, there's nothing convenient. You can pull out the calculator and figure it out. Okay, 4, this is positive, this is positive, this is positive, so false. So my region here is this open interval from 0 to 1. The union of that, the open interval from 1 to 3. Which again I could write as x such that x is less than 1 and greater than 0, or x is greater than 1 or less than 3. And again, my graph is going to look like this. There are 3 points missing, and then there are these 2 open intervals. I'm going to give you just, oh no, I don't have to. I have an example of what I was thinking of. I know this is going to be in your way a little, but I want to get this warmed up. Okay. One more problem here, like this. Here we have a rational expression, 1 plus x over 1 minus x greater than or equal to 1. 1 plus x over 1 minus x minus 1. And subtract 1 from both sides is greater than or equal to 0. I'm going to put this over a common denominator. 1 plus x minus 1 minus x, which is minus 1 plus x minus x greater than or equal to 0. So I end up with 2 over 1 minus x, which is greater than or equal to 0. So here I only have one critical point, which is 1. So when I do my table, I'm going to have to look at something less than 1. So let's say 0. So 0 would be 1 minus 0 is 1. 2 greater than or equal to 0, so that's true. Let's see, where's 1? So this region is going to be included. At 1, I'm undefined. False. In the next section, if I plug in, say, a 2, I'm going to get negative 2 greater than or equal to 0, which is false. I'm missing something here. Oh. In my haste, I forgot, this is 2x. So that means 0 is also a critical point. So I actually have to look up here at minus 1. So 1 minus minus 1 is 2. Minus 2 greater than or equal to 0 is also false. I didn't do this very well. I apologize. So basically, I have this region here, nothing. This region here, nothing. 1 is excluded, and this region from 0 to 1 is included. So this is the half-open interval 0 to 1. This goes to your question about when the undefined come in, right? Because in this case, 1 minus x, you can't use 1. So it's a critical point that you can see. It is a dividing line, but it's not included. We okay on this? Are there any questions? I have a couple minutes left.